Picture an aircraft tearing through the upper atmosphere. At these speeds, friction from the air alone generates enough heat to compromise standard aviation metals. To survive that environment, engineers rely on a specific material, element 22 on the periodic table, titanium. It offers a rare mechanical profile. It is lighter than steel, but maintains incredible structural integrity, and it aggressively resists high temperatures and corrosion. But you will never find a pure piece of it rusting on the ground in nature. When exposed to the elements, titanium immediately and aggressively bonds with oxygen, locking itself into an oxidized structure. This chemical reflex is so persistent that the metal spent thousands of years completely hidden from human civilization, trapped inside ordinary stones. In the late 18th century, an English clergyman named William Gregor began examining a deposit of strange black sand near a stream in Cornwall. He had stumbled upon ilmenite, a dark, jagged mineral. A few years later, German chemist Martin Heinrich Klaproth independently studied similar samples and realized these raw, metallic chunks were hiding an undocumented element. Recognizing the dense, durable nature of the locked material, Klaproth named it after the powerful ancient beings of Greek mythology, the Titans. The metal is also frequently trapped inside rutile, a layered, translucent orange-brown mineral where titanium and oxygen remain tightly bound together. Assigning a mythological name to the element was a simple task. Severing the chemical bonds to extract the pure metal was so difficult that titanium remained a mere laboratory curiosity for another 150 years. The deadlock finally broke in the 20th century. Scientists developed the Kroll process, a complicated, multi-stage chemical extraction method that could at last separate titanium from oxygen efficiently. This breakthrough allowed manufacturers to produce pure titanium at an industrial scale, turning fiery smelting furnaces into processing hubs for element 22. For engineers, this newly available metal solved a persistent mechanical problem, the strength-to-weight ratio. As you can see in this comparison, titanium can provide the structural durability of a massive block of steel at a fraction of the mass. By making this specific ratio commercially viable, the Kroll process pulled titanium out of mineralogy textbooks and placed it directly onto the assembly lines of modern aerospace. The timing was critical. As the Cold War and the space race accelerated, engineers pushed machines to fly higher and faster, subjecting airframes to intense mechanical stress. At supersonic speeds, atmospheric friction generates severe aerodynamic heating. Standard aviation metals like aluminum begin to soften and lose their structural integrity under these thermal conditions. Look at the Lockheed SR-71 Blackbird. To maintain stability while flying near the edge of space at 3 times the speed of sound, its designers built the majority of its airframe out of titanium. The same thermal and mechanical resistance made it essential for early space exploration, as technicians relied on titanium components to construct spacecraft capsules that could survive the violent pressures of launch and the deep freeze of orbit. The metallic dust that William Gregor found resting in an English stream was now holding human engineering together at the very edge of the atmosphere. Beyond the vacuum of space, titanium found a role in a completely different, highly sensitive environment, the interior of the human body. The element possesses a trait called biocompatibility. That aggressive reflex to bond with oxygen, the same trait that trapped it in rocks, causes pure titanium to instantly form a microscopic shield of titanium oxide on its surface. Inside a patient, this oxide layer acts as a neutral wall. It prevents the underlying metal from reacting with bodily fluids, meaning the human immune system is highly unlikely to recognize it as a foreign threat. This X-ray illustrates how structural medical hardware, like a complete hip replacement, relies on titanium to integrate directly with human bone for decades of weight-bearing use. We also see it in delicate, small-scale procedures. Dental surgeons implant threaded titanium posts directly into the jaw to serve as artificial root structures for teeth. Element 22 maintains its structural integrity under hypersonic friction, while simultaneously allowing human bone tissue to grow directly onto its surface. It serves the high-altitude airframe and the dental patient with equal reliability. Despite its utility, titanium is still difficult to manage. The extraction and machining processes require massive amounts of energy, making the metal highly expensive compared to steel or aluminum. To reduce this waste, modern engineers are turning to additive manufacturing. By 3D printing titanium layer by layer, designers can construct highly complex custom lattice structures for medicine and aerospace using exactly the amount of metal required, and no more. And every ounce of that material traces back to a cosmic origin. The heavy atoms that make up element 22 were forged in the immense heat and pressure of ancient stars, long before our solar system formed. Those stellar fragments drifted into the Earth's crust, weighted beneath the soil in ordinary rocks, and eventually became the structural foundation for both high-altitude flight and human biomedical recovery. Titanium proves that highly capable materials often sit unrecognized in the mud at our feet. With 96 more natural stories on the periodic table, the next ordinary rock might be hiding something even more surprising.